In this video, I want to talk about the rubidium-strontium decay method of determining radiogenic dates. So, quick review, we know that for radioactive decay, the rate of decay, dN dt, is proportional to the number of parent atoms, the radioactive parent atoms. These are the parents here, right? And the decay constant, the proportionality constant, sorry, is called the radioactive decay constant. And if we integrate that, we get this expression here. For the number, these are the number of parents. I should write that. These are the number of parent isotope atoms as a function of time. And we talked about how that's just a radioactive decay curve, right? So if I were to plot that amount, it would look like this. It would asymptotically approach 0. Now for rubidium-strontium, rubidium-87 is the radioactive parent. It decays to radiogenic strontium-87 by beta decay. So that when I talk about P and I talk about D, I'm talking about rubidium-87, and the daughter is strontium-87. Just a quick review of what this looks like on a time graph here. So in red, I have the amount of radiogenic daughter. In blue, the amount of radioactive parent. And since one parent decays to one daughter, we see these two curves that look like this. Decay curve I described earlier for the parent, an increasing concentration of the daughter, and at any given time is along the x-axis, right? The two of these will sum up to the original amount of the parent that was present before radioactive decay started. Now, in theory, if you look at this, you can say, well, then the ratio of the parent to the daughter or the daughter to the parent, well, that ought to be proportional to the age. And indeed, that's true. Here I've just plotted up on the exact same graph the daughter-parent, this is daughter-parent ratio. Which goes from 5 up to 35, and these are the number of half-lives or number of years in half-life increments going by along the x-axis. And the point I want to make is really simple, that yes, this ought to work, right? Though if I can measure the ratio of daughter to parent, I should be able to relate that to an age. So in theory, that's how radioactive decay schemes work. I measure the amount of the radiogenic daughter, and I measure the amount of radioactive parent present in my rock. I look at the ratio of those two things, and if it's really enriched in the daughter, then a lot of time must have elapsed. If it's mostly enriched in the parent and there's just a little bit of daughter, then not much time should have elapsed, and therefore I can back out the age of the rock. Another way to show this on a different type of graph that loses a little bit of information but shows other kinds of information is to graph the radioactive parent here versus the radiogenic daughter here, and look at how that position would change with time. So initially it's the blue dot here, there is no radiogenic daughter, and with time, as time goes by, we're going to increase the amount of radiogenic daughter and decrease the amount of radioactive parent. And since there's a one-to-one relationship, this line that shows the path of the rock as time passes should have a slope of -1. So the youngest rock plots at the bottom right, and the oldest rock plots in the upper left, and this has a slope of -1. What's lost on this diagram, by the way, is the rate of movement along this line, which is actually decelerating, because remember, the higher concentrations of parent have a faster decay rate. So as we move along the line in that path, the actual movement should be decelerating. But that's not really important for this diagram. It's just basically showing you how the two things you can measure here, the amount of radiogenic daughter and the amount of radioactive parent, are changing through time. And on this diagram, the age is proportional to the length of time, the length of the line that connects us from here's where we started, right? The starting composition, which was all radioactive parent and no radiogenic daughter, to the end position, which would be less radioactive parent and more radiogenic daughter. So the length of that line is proportional to the age of the rock. Now, the problem here with many decay schemes, including rubidium-strontium, and this is why we're going to talk about rubidium-strontium, is that there's a big assumption here that is almost always not valid. And that is, we are assuming here that initially there was no radiogenic strontium present in the rock. And that's almost always not true. Okay, initially we assumed that there was 0 radiogenic strontium in the rock, so this point, this composition of the rock, right, in terms of the parent and daughter plotted right along the x-axis. And that all of the decay then produced all of the radiogenic strontium in the rock, which we ultimately see, was produced by decay, right? But what happens if the amount of radiogenic strontium in the rock wasn't zero before decay started? So here we have a situation where here's my rock plotting, this is my initial composition, and now it has some amount of radiogenic strontium in it. Now, as decay proceeds, radioactive strontium is going to decay to radiogenic strontium at a 1-to-1 rate, so we're going to get a slope of -1, but we're going to head off in this direction like that, right? And once again, we can say, yeah, it's all going to work exactly the same way. We're going to get a slope of -1, and the age is going to be proportional to the length of this line, right? But the problem is, we don't know what that line is. All we measure in our rock, when we go sample our rock, we take our rock back to the laboratory, we measure the amount of strontium-87, we measure the amount of rubidium-87, and the rock plots on this diagram, and we don't know where the composition started. In other words, this combination of radiogenic strontium and radioactive rubidium could have started right here at an initial composition pretty close to the final composition, so that in order to get there, not much time elapsed. Or it could have started from a position here, where it took much longer to go all the way from the initial composition to the final composition, and therefore we infer that more time has elapsed. The rock is older, and we don't know which of those is correct. Now, it turns out that this is a really common situation for decay schemes like rubidium, strontium, and actually many others, where there's a possibility that the initial rock has some amount of the radiogenic decay in it. And we have to think of a different way to approach the problem now that we have an additional unknown. And that approach uses something called an isochron diagram, and that's going to be the focus of the next part 2 of this sequence.